All right, everyone. Welcome to another presentation from the Wolfram Institute. Today, I'm quite excited to be introducing Fernando Méndez, who's going to talk about release structures and graph writing. So this is a pair of topics that is very close to my heart. My background is in Poisson geometry and the algebras, so I'm very happy to have representation of the Lee crowd here. And of course, I am now very invested into graph writing, hypergraph writing. So I'm very eager to see what's on offer here. I'm very excited to see Fernando. So please take it away.
Okay, so yes, first of all, thank you very much for this opportunity of sharing my project. I think I have met most of you in Boston, but to those whom I don't know, it's so nice to meet you. So yeah, as Carlos said, my project is about the Perl structures of graph rewriting. So let me give you a little bit overview of the presentation. So first, I will give a brief introduction slash motivation of the problems we tackled in this project. I will talk about something we call the context-free case. Then I will talk about the context-sensitive case, and finally about the associated Axiom systems. So let's start. Okay, just a quick comment. I prepared this presentation in such a way that everyone who's familiar with mathematics, but not necessarily with mathematics, can follow it. But I will switch to the community post when necessary. So having said that, let's just begin. So yes. So to start with, let's start with something very simple. Suppose you have an algebra. So that means you have a vector space A together with a linear product. Okay. And of course, now that you have this product, then you can define an operator called associator, which is defined this way. I mean, the definition is it's pretty suggesting. And of course, if your algebra is associative, then this guy is always zero, and there's nothing else there's nothing interesting we can say about the associator. So let's assume your algebra is not necessarily associative. So a natural question is, if the associator is not associative, then what is the next best scenario for the associator map? If you want, think about it for a few seconds, and once you have some kind of idea, let me propose you the following a scenario. So maybe A is not associative, but maybe you can get this a very nice scenario. So suppose you have a permutation, a fixed permutation that we denoted by sigma. Okay, then let's impose the following condition. So again, maybe the algebra is not associative, but maybe we have this symmetric condition. Okay. So the permutation is kind of acting in the associator. And the point is that the first examples and studies of these kind of structures appeared in a work by Arthur Cayley back in the 1800s. And in such work, the case for this transposition was considered the transposition 1-2. And those algebras for which such equation was satisfied for any of those transpositions 1, 2, or 2, 3 are called Pauli algebras. And in particular, if you have the transposition 1, 2, then the algebra in question is called left symmetric. Now, the reason we use the same name for any of those two transpositions is because you can get one from the other. So in other words, if you have a left symmetric algebra, you can get or define a right symmetric algebra by just switching the definition of the product and the other way around. So in some sense, they are the same structure, right? So having said that, let's talk about what we call the context-free case. So let us consider the set S of all directed, acyclic, and connected graphs. Okay. Yeah, and consider any, yeah, and that's for short. Okay, so and consider any two graphs, G1 and G2, in S. Okay. Now we can construct another graph in the following way. So consider your favorite vertex V of the first graph and the root that we denote by V2 of the second graph. Then we can construct this graph that I denoted this way, G1 left triangle V G2, which will be the result of gluing the second graph into the first one by identifying, watch out, not replacing, identifying the vertex you chose with the root of the second graph. So graphically, this looks like this. For instance, suppose G1 and G2 are the following graphs, okay? And in the first case, we have chosen the vertex 5, okay? In the second case, the root is 18. So according to the rule, we have to identify 5 with 18, and then glue the second graph into the first one, okay? So clearly this will look like this. And I used this notation to make emphasis on the identification of the vertices, okay?
Can you show that again?
Yes.
Can you go back one?
Yeah.
Okay, so you have this, you're trying to splice that in, or you're trying to augment, wait, so G1, and you have a vertex selected, and G2, so you're making this operation, this a left triangle operation, right?
Yes, there's one right here for the vertex 5. So you pick 5, you pick the root of the second graph, which is 18, you identify them, and then you glue this graph, which is the first one. So you get this, right?
Five and 18 are unified, and then what happens to the branch going to 19?
It's
Okay,
right
okay,
here.
I see. So you have, okay, so you're just
Right, just in a
you just graphed it on then.
Yeah, just displayed in a different form, but yeah, it's all the vertices are there.
Yeah,
okay?
yeah.
Okay. Then and now remark that the root of this new graph is 1, okay? The vertex 1. Okay. Okay, so far pretty easy. So next, this product depends on the vertex V we chose. So one way of defining a product between these two graphs, which is somehow dependent of the vertex we chose, is the following. We make the same construction for each vertex of the first graph, and then we consider this sum, right? Now let me just make a quick comment on something I am asked like 50% of the times I talk about this, which is how do I define the sum? Which is of course a very natural question. And the answer is that this sum is a sum on the free vector space generated by the set S. So in other words, it's more like a formal sum, not a arithmetical sum. Okay.
Hold on, so it's not the sum of adjacency matrices of graphs.
No.
Sorry?
No. It's more like a disjoint union.
Yes, it's more like a disjoint union. Or like a sequence if you want to.
Yeah.
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 Okay, like a sequence of graphs.
So just to make things simple, so this is basically telling me take all your vertices from G1 and basically splice it in all these possible ways and just consider all those new graphs together, right?
Right.
Right. So which product it is? Is it like that has a name? There's many graph products. Is it like a Cartesian product or something else?
No, it's not a graph product because the output is not a graph.
Yes.
Oh, I see. Oh, okay.
Yes, it's not a graph. It's a collection of graphs.
Yeah.
And this is predicated on the the thing that you're splicing on having a preferred vertex. as a root?
Well, notice that for each term, each time you construct this graph, the root of this new graph will be the root of the first graph. So
Okay, so but DAGs don't necessarily have a single root.
yes. In that you are totally right. So in this case, what we are doing is, since we are working with integers, we are just considering all the graphs which have incoming edges, and we are taking that which has a minimal value. Okay. So just
yeah.
keep the first one.
Well, I mean, let's see. I mean, you can always, yeah. I mean, you can have.
Yeah. So
Like,
so I
yeah,
think
I don't know.
just because this is just the setup, so we make sure we move on. So this is simply a common thing where you define a formal sum in the expectation that you're going to build something like an algebra, right? Like an algebra, you first need a way to add things together because you're a vector space, and then you need a way to compose things.
Mhm.
So it is kind of like a first step that if you know how to compose things, because we just Fernando here just introduced this splicing of graphs. So throwing things into a formal sum basically is going to allow us to use linearity and sort of throw different graphs around, and things are going to behave instead of thinking more in pure set theoretic terms. We're thinking in terms of, if I have two graphs and one is positive and one is negative, I can cancel them out, kind of thing, right?
Oh, that's not what I'm worried about. Oh, well, I'm just thinking like with these DAGs, a DAG might not have one single root or
No,
one single minimal vertex.
I don't think that's really important, because here the point is that you have graphs and these objects you can abstract. Like, it doesn't really matter what these objects are, as long as you, I mean, Fernando, correct me if I'm wrong, but I think all that's happening is that you have a graph and you have a way to compose it that is clearly asymmetric, right? Therefore, this sort of notation with a triangle going in one direction. And I mean, the construction requires the specification of one vertex. So that makes it a little bit too specific of the naming of a vertex, and we don't like that. So this is a way of basically getting a way of just having to use a vertex to construct, and you just say, okay, do all those constructions and just consider the formal sum of all those possible outputs, and that is it's more than a single graph. It's like a set of graphs, but if you put it into a kind of linear setting where you can consider each object two times, that's like twice this, and this object three times, this is like a vector, two times this one plus three times that one.
Mhm.
And it's just basically a kind of a very common trick, like this idea of like free groups and free rings and things like that, where you have a base set and you just generate something freely out of that base set, right?
Yeah. I'm with you on the formal sum over
You're
over
probably
field of
you're
scalars.
saying that the root is not unique, right? That's your concern.
For G2,
Yeah.
the root might not
Yeah.
be for a general DAG. Like you're not guaranteed that you'll have like this red vertex at top.
Yeah, I mean, I agree. There is no one only root. But what we are doing here is that, I mean, since we are considering just vertices with integer values, we just select the root which has the minimal value.
Yeah, I mean you can in a DAG you can start at like any vertex and then figure out what arrows are pointing into it, and then go up, let's say, to the previous one, and then keep going until you keep until you stop. I guess if we're dealing with finite DAGs, and then you'll stop eventually, and then you can call that one of the roots, but you're not guaranteed. I mean, you can have two vertices going to one vertex with down arrows, and so it's not determined which one is is there. But if you number the vertices, then you just take like the smallest value.
Would it help if Fernando maybe continues with the
Yeah.
presentation, we come back to this point? Yeah.
Actually, later on I will find an example of the kind of case that Dugan is mentioning. So yeah, I will talk about that a little bit more later on.
Mhm.
So yes. So again, this gives us a linear product on this free vector space generated by S, and therefore we get an algebra. So, moreover, if we define the commutator of two graphs the usual way, so that means the commutator of G1, G2 is G1, G2 minus G2, G1, then this free vector space with this bracket is actually a Lie algebra. So what does that mean? Following conditions are satisfied. The first one says that this bracket is antisymmetric. That's pretty clear from the definition. And the second one is that the Jacobi identity is also satisfied. Maybe that second condition is not clear at all.
Yeah. One quick question, maybe also to reinforce your presentation here. Is this product associative?
No, it's not.
That's super fascinating.
Yeah. So so the natural question is, okay, so how do I prove or how do I verify the second condition in a smart way, right? So instead of course, computing using brute force, right? So to answer this, the trick here consists in noticing that in any algebra, it can be a Clifford algebra, Lie algebra, Jordan algebra, derivative algebra, if you define the commutator in the way we just did, so that means the commutator of A and B is AB minus BA, then the following equality holds. The Jacobi identity can be written as this sum of associators. And here, this guy denotes the sign of the permutation in question.
Yeah. But this is for the case where the algebras are antisymmetric, isn't it?
Any algebra.
Okay, this is okay. Not assuming antisymmetry. Okay.
I mean, but of course, note that in any algebra, if you define the commutator that way, the commutator of AB as AB minus BA, then this commutator is antisymmetric.
Sure.
Then with this bracket, this condition will hold in any algebra. I mean, you just have to define this commutator in that way. So therefore,
wait. So wait. I'm a bit confused. So is the commutator on the right hand side? So the associator in the right hand side for the dot product or for the bracket product?
For the dot product.
Okay.
Yeah.
Okay. I see.
Yeah. For the dot
What you're
product.
saying is that this doesn't necessarily assume antisymmetry of the dot product.
Yes.
Okay.
Right.
Sure.
Okay. So therefore, if for example this equation holds, I mean we have the symmetry condition I wrote at the outset of the presentation.
Mm-hmm.
If this condition holds for a fixed permutation, then that means that the algebra becomes a Lie algebra because each term will cancel out with some other term.
Yeah.
So that's the way we prove the algebra we just defined is a Lie algebra. So in this case, it turns out that if we consider this transposition, the transposition to 3, then this equation will hold for any elements of the free vector space. And of course, it's enough to verify this for the basis, and the basis is all the elements of S, right? So the first step in order to prove this is to note that this term can be written as these two sums. And the reason for this is that remember that once you compute the product of G1 and G2, you get a collection of graphs, but these graphs have vertices in both vertices in the set of vertices of G1 and the set of vertices of G2. So clearly you can decompose the sum as, you can decompose this product as these two sums. So the first the first sum considers only vertices in the first graph, and the second sum vertices in the first graph and in the second graph. So
But-
similarly,
So I'm
Yeah.
confused. Should it? Right, I see. Okay, no, I understand.
okay, perfect. Okay, so in a very similar way, if you compute this product, then you can write it in this way. This sum over all the vertices in V in G1 and all the vertices U in the set of vertices of the second graph. And here the key observation is that provided V belongs to the first graph and U belongs to the second graph, we get this associative condition. So for instance, watch out. That doesn't mean that the product itself, this guy, is associated, but it's associative with respect to the
First of elements.
yes.
Right, and I guess that's intuitive, because at the end of the day, what you're doing is splicing three graphs together, right? So the result is unique,
Right.
right? It doesn't matter that you splice this and then these other two, because the splicing of the first with the second one and the third is the same as you first do the second and third together and then splice, right? Because these splicings are the way they are defined, they are sort of independent.
Right. So to illustrate what Carlos just said, remember that the vertex B we chose at the outset was the vertex 5. So now let's consider a vertex of any vertex of the second graph. So let's say 19.
Yeah.
And let's consider another third graph, another tag, which is this one. In this case, the root is 20. So what was I saying to Dugan earlier on was that in this case we have three nodes with without incoming edges, right? So 23, 20, 22, and 20, right? So those are roots. So we are just picking, choosing the one with the minimal value, which is in this case 20, right? And that's it. That's the way we are choosing the root each time. So having said that, according to the rule, remember that in the first case we computed, we identified the vertex 5 with the root 18 of the second graph. So if we compute now this product, G1, G2, and G3 with respect to the vertices B and U, then we clearly get this. Since according to the rule, we have to identify the root of the third graph, which is 20, with the vertex 19. So we get this identification in this case. And now, if we compute the other graph, so that means first G2 with G3 with respect to the vertex U, and according to the rule, again, we have to identify 19 with 20. We get this graph, and now the root is 18. So that means that when we compute the product with respect to the vertex 5 of the first graph, we have to identify the root, which is 18, with the vertex 5. So we will again indeed get this graph, right? So yes, that means that that equation will hold, and therefore the associator of these three graphs will be given by this sum. So we just have to sum over all the vertices of the first graph. Okay, and similarly, we get this equation. So that's the other associator, and now we have to see somehow that these two associators are equal. Now note that this term, watch out, only this term, not the whole sum. This term is not necessarily equal to this other term. For instance, if we choose the vertex U equals 2, then according to the rule, we will have to pick the root of the third graph, which is 20, identifying it, and then to identify it with the vertex 2. So we will get the vertex 2 identified with the vertex 20, and in the other case, we will get the vertex 18 identified with the vertex 2. So we will not get the same graphs. So the trick here to show that these associators are equal is to note that we just have to switch. So in other words, this term G1 left triangle U G3 left triangle V G2 is equal to this term. So we had to switch, right? And I think I have an illustration of that in the community post, but in order to not take too much time on this, I will just continue. And of course, now the motivation importance of this construction is twofold. On one hand, from the mathematical point of view, and more precisely from the algebraic point of view, this gives us an example of an infinite dimensional left symmetric structure. I will give the definition of that later on, don't worry. And from the point of view of physics, it turns out that this very same product can be defined on a special class of Feynman diagrams called one-particle reducible Feynman diagrams. And this provides you an algebraic approach to renormalization in quantum field theory. Now, I'm not a physicist, I am a mathematician, so I will just focus on the first point. If you want to know more about the second point, the best idea is probably talk to Cersei or to one of the papers I will, or to check the papers. One of the papers I will drop in the end. So let's focus for the moment in the first point. And regarding the first point, like I said, these structures were born with the work of Cayley, but these structures received a very important attention in 1977 when John Miller, the Fields medalist, formulated the following question, which is it true that every solvable Lie algebra admits a complete left symmetric structure? So of course, since John Miller was the one who asked this question, everyone was trying to solve or give a counterexample to this conjecture. And since then, the study of this structure has been a very active line of research. And like I said before, this has proved to have remarkable applications, not only in physics, but also in geometry. Actually, John Miller formulated this question in terms of differential geometry, but I'm an algebraist, so I just translated the question in terms of algebra, which is the branch I understand. So now let's talk about those left symmetric algebras I told you before. So like I said, if you have a left symmetric algebra, you can endow your algebra with a Lie structure by just defining the commutator, the Lie bracket, in this way. So a very natural question is, okay, let's start the other way around. So in other words, assume you have a Lie algebra G, and the question is, can I find a bilinear product denoted by a dot product, such that the Lie bracket can be expressed in terms of this dot product? So in other words, is my Lie bracket a honest commutator? So in other words, more precisely, given a Lie algebra G, is there a dot product such that with this dot product, G is a left symmetric algebra, and the Lie bracket on G can be expressed as well, this way? And it turns out that in some cases it's possible, in some cases it's not possible, but when it's possible, the Lie algebra in question received the name of left symmetric structure. Okay, so having said that, now let's talk about the context-sensitive case. And now the point is to work not at the vertex level, but at the subgraph level. So in other words, we try to generalize previous product as follows. Again, you have three DAGs, G1, G2, and H1. And if the first graph contains as a graph H isomorphic to the graph H1, and we can obtain a new graph that I denoted this way, R G1 H G2, by just replacing that copy of H with G2. So this is like the kind of rewriting rule we consider in the Wolfram Physics project, right? So they suggest to define this product that I denoted this way as the sum. So what we do is we search within G1 all the copies that are isomorphic to H1, and we compute this new graph, okay? So it turns out that in this case, okay, so, and the natural question is, okay, what do we do if G1 does not contain a copy of H1? Then in that case, we just define this product as 0, okay?
Can I ask something quickly? So just to understand what is going on exactly, because so G1 and G2 are arbitrary DAGs. Then G1 is, if it contains a subgraph isomorphic to H1. So don't you need some condition on what replacing means here? I mean,
yeah, I mean, you have, yeah, I didn't say that, but you have to define a replacement in a consistent way.
yeah, because I mean, if you know, if you're like, most people will be thinking intuitively, I mean, I am thinking intuitively that you find a subgraph and that subgraph has a boundary, so to speak.
Yeah.
Connects it to the
a vertex color, you mean, right? Like a vertex color.
Yes. And so it's certainly not the case that given a as you call it, a vertex color, right?
Yeah.
Given a vertex color, it's certainly not the case that for any arbitrary graph G2 you can splice it there in a canonical way, right? There's
yes, you're totally right. There's no way.
Okay. No, I'm just asking to make sure that I understand what's going on. Yeah. So how should we be thinking of this particular construction?
Yes. Well, short answer is that you just have to choose a replacement which is consistent each time you consider this product. But because, like you said, there is not only one way to do it. And yeah, this is something I had. I was struggling the whole summer, but
yeah. But I think that's okay. I think I don't want to stop the presentation at all. I think, but it's important to understand that that's a point where there's ambiguity, and that, of course, this comment that when you say that H1 G1 doesn't contain a copy, it might, I imagine, and correct me if I'm wrong, but I imagine it might also be the case that G2 might just not fit in the context where H happened. And in that case, you just might assume that the result is also 0, right?
Right.
So I can imagine that with a combination of when things don't match, you output 0, and when you have several equivalently well-defined splicings, you just throw them into the formal sum, right? With a combination of those two things, I can definitely agree that you can define such a product. And I guess that's good enough for our presentation today. Probably.
Yes.
Okay.
I think it's essentially a differently written rewriting rule. It's like I would just think of G1 as your initial graph that you're trying to rewrite, and H1, G2 is like left-hand side and right-hand side, essentially like a rule. So if you right?
Yeah,
so
well, if that's the case, but then if that's the case, then it's something much stronger than what we're saying here. Because if that's the case, then H happens in both G1 and G2. Right?
Why? G2 is the right-hand side of the rule.
Right.
And H1 is the left-hand side that you're looking inside G1, right? So we're just looking all the matches, which is H, right? We're just looking for all the matches, which are all the H's that you're summing over, and you essentially just constructing all possible matches and all possible rewrites.
Well,
It's like
but the
yeah.
problem, but the problem is that you need more information to define a rewrite rule. You need more information than just input output, right? You need to tell the rule what is.
Yeah, well, that information can kind of, if you encode it as in a hypergraph, like we have in the hypergraph package, right? If you have a right hand side and left hand side.
No, of course. I mean,
Divide as hypergraph.
You can encode it, but I mean, in mathematics, when you're defining mathematics, you need to say there is something that gives you that information, right? You can't just say, yeah, it's gonna be somewhere. So, in that sense, you need to say, the occurrence of H in G1 is going to delete this subgraph of H, and it's going to preserve this other subgraph of H, and then that preserved subgraph is going to be also part of G2, and then the rest is flipped in. It's the usual sort of like.
Yeah, well, I understand, but usually it's like if you actually want to encode it, like we don't actually have this information, right? You can we can specify the rule by just specifying two graphs, and all the information what's being deleted and being rewritten is just in the vertex names essentially, or labels. You don't even have to have labels. You just have to have some information that identifies some vertices on the left hand side or on the right hand side.
I don't think that's true. I disagree that you don't need I mean, if you're saying that you just need two graphs to define a rewrite rule, that's just not the case, right? Because two graphs don't tell you how to replace a subgraph, right? It tells you how to detect a subgraph, but once detected, you have another graph that doesn't tell you at all what to do with it, right? You need some other.
Know the identification between vertices on the left and the right of the rule.
Well, that's a lot of information. That's more, right? That's
not
just
more. That's what I said. You have the vertex names that identify which are. That's the only condition essentially. It's not just
but that's a particular case of what I'm saying, right? It's a particular case of a context.
Yeah. Oh, whatever. Let's just continue. Just.
Yeah. I think we are on the same page. So basically, a summary just to move forward is that we can make this more precise, either by Nick's suggestion that we make this into a formal rewrite rule as we normally do, or maybe by considering all possible canonically defined ways of splicing, and when things are not well defined, 0, and when they are many, you just throw them into the formal sum, right?
Right.
But in either case, there is a way to give a well-defined product.
Yes.
Okay, good. I think we can move on.
Okay. Okay, so what we're trying to point out here is that even if in the nicest cases, we don't get a symmetry which was in the associated condition. We don't get that kind of symmetry. For instance, consider that very simple example. So G1, G2, and G3 are those two graphs. So G2 and G3 are basically edges, and G1 is just that graph, okay? And we consider the graph H1 as an edge, right? A directed edge. So in this case, clearly H1 is isomorphic to G2 and G3. That's a mistake. I wrote G1 and G2, but it's G2 and G3. So on one hand, I mean, if we compute that product, then clearly the first graph contains two copies of H1. So in this case, there is no possible ambiguity on how we should do the replacement. So since we have two copies, we have two summands, and we got this, right? Consequently, that product will be given by this sum, and in a very similar way, we get this, okay? And that's because G3 is isomorphic to H1 and isomorphic to G2, right? So that means that on one hand, the associator of G1, G2, and G3 is given by that graph, well, 2 times that graph. And on the other hand, the other associator is given by that graph, okay? So technically, look, take a look at the both graphs. Technically, they're not the same graph. I mean, the vertices are different, right? They're isomorphic, but they're not the same graph. So that means that at least with this kind of replacement, we cannot get a Briley structure. So the problem is that one of the issues with this kind of rewriting is that we lose information about the labels of the graph. In this case, if we had identified as before, we would have gotten the same kind of the same result. Nevertheless, even if we identify labels, this product still does not define a Briley algebra on the corresponding vector space. Actually, it can be proved that no matter how you define your replacement rule, if H1 is any graph, then you can always find three graphs, G1, G2, and G3, such that those associators are not the same. So now let's talk about the axiom systems. So maybe, yeah, I'm pretty sure that each and every one of you are already familiar with the idea that Stephen wrote in his MetaMath book, but that's not necessarily the case of every person who will watch this live stream. So let me talk about a little bit about that. And the idea is the following. So as you know, let us consider a non-empty set that we denoted by A, and we have a binary operation that we denoted by a circle. And we suppose that the following axiom holds for any elements x and y. Okay, so x circle y is equal to y circle x circle y. And now suppose that we are given an initial state. In this case, A and B are fixed elements, and we consider this initial state. So the question is, what happens if we apply the above axiom in all possible ways? If we do it once, we get this. Perfect, easy enough. If we do it twice, we get that multi-way graph. If we do it 5 times, we get that pretty chaotic multi-way graph. So, but the point here, or at least one advantage of this computational approach, is that you can find equivalences between expressions. So, for instance, you can prove that those two expressions are equal, and you can prove this by just exhibiting a path in the multi-way graph. So, well, in that case, that will be a graph. So that will be a graph and the corresponding path. So in general, what I'm trying to point out here is that in general, it's very hard to prove whether a Lie algebra has a length symmetric structure or not. And one of the most classical approaches is the following. So, okay, you have an n-dimensional algebra G, which admits a left symmetric structure. Sorry, you have a algebra G, n-dimensional. And you can prove that G has a left symmetric structure if and only if G has a representation, rho, such that G has a non-singular one-to cycle with respect to rho. So of course, the problem or the potential problem with this theorem is that first, you need to find a representation. Second, once you have found the representation, you need to compute or at least understand your space of one-to cycles, and then you have to look for those one-to cycles that are non-singular. So one might think, okay, maybe with this computational approach we can study these kind of algebras and maybe find another result which is not that complicated, right? So we tried this and we consider this two-dimensional algebra A and B. So the base, it's two-dimensional. The basis consists of A and B, and we define the product in that way. A is 0, AB is 0, BA is minus I, and B dot B is A minus B. So this approach, in fact, allows us to prove that A is a Briley algebra. So what we have to do is exactly the same we did before. So in that case, we consider this initial state, which is just the associator ABA, right? And yes, again, you apply the axioms in all possible way. After 2 steps, you get that pretty crazy graph, which is natural because if you think about it, before we just had one axiom. So we had a very simplistic kind of a structure. But an algebra is much complex because I mean, you don't have not only the axioms of a group, but the axioms of a vector space, right? Plus the definition of the algebra itself. So, yes, the point here is that using the same trick as before, you can find paths between the associator ABA to the associator BAA, and graphically this looks like this. And you can do the very same thing with all the other associators left. So, to conclude this, let me talk about the future end-to-end work. The first plan we are trying to do is to study the algebras that satisfy that relation for a fixed permutation, but this permutation needs to be different from those two. Okay. So, for instance, a very interesting permutation one might consider is the permutation 1-3, right? Second, some examples suggest, like I said before, that in the context-sensitive case, if you do along a common graph, instead of just replacing everything, and you identify the corresponding labels, and then the three graphs have at least one copy of H1 within themselves, then the associator will be symmetric with respect to some permutations and some families of graph. And third, to study the context-free case for hypergraphs. I mean, we have already understood the graph case, so the next logical step is the hypergraph case. And last but not least, an optimization or aberration of that function. Well, needs to be done in order to study those higher dimensional algebras. And the reason I'm telling this is because the code, I mean, I didn't put it here, but it's right here. You can see the code, right?
Yes.
Yeah. Well, that code for 3 steps took 3 hours. So yeah, it's fun in the summer school because I had to carry my computer for several hours just to run that code. And of course, again, this is due to the large number of axioms that an algebra has. But provided that this last stack is achieved, the resulting functions might help to study higher dimensional algebras with a richer structure, which admit really structures. So for instance, symplectic algebras, Riemannian algebras, quantitative algebras. And yes, so that will be it. If you have any questions, please go ahead.
Well, amazing, Fernando. Thank you very much for the presentation. I think this is, yeah, as I said in the beginning, it just marries my two favorite subjects, at least historically. So I'm quite excited. I'm quite curious about. So, I mean, this to me is fascinating. The fact that you have. I actually learned this from Mano, who's well known in the Wolfram sphere, that these algebras are. I find it very interesting that you have a commutator of a non-associative algebra that gives a Lie algebra. That already to me is remarkable. In the very first case, I'm familiar with the background for the left symmetric algebras, but so this whole Milnor problem that you presented, it was a bit lost to me. I didn't know exactly why. I mean, it's a natural question to ask, of course. Yeah. But I didn't get any sense of why it is such an interesting question to ask. Do you have a sense of why?
Actually, like I mentioned, Milnor asked this question in terms of geometry. So apparently, in differential geometry, there's something he calls affine structures, and yeah, apparently this algebraic question gives us a lot of information about those affine structures. Actually, there is a correspondence.
Oh, you mean affine structures?
Yes. Yes.
Affine structures. Okay, right.
Yeah.
I see. Interesting. Huh. I see. Okay. Yeah, well, that's interesting. My other follow-up question is, I mean, you already pointed at it, but it's funny because I mean, the reason I'm here today talking to these guys and involved with, Wolfram stuff is because I was at some point studying Lie algebras, right? Like the causality, if you analyze the causal graph, you actually find in some of my past notes, you actually find Lie algebras as kind of like the identifier. And of course, the way I got into this is that when you try to generalize to ternary Lie algebras, I mean, these are algebras that are fairly well understood, where you simply you have to be a bit what is the word? You have to be a little bit disciplined with how you write your Leibniz rule in order to, or your Jacobi identity.
Yeah.
So because otherwise you get into trouble. But if everyone agrees that the Jacobi identity is, in absence of antisymmetry, is the fact that a Lie bracket is a self-derivation, right? That when it acts on itself as a linear map, it acts as a derivation of itself, right? And everyone can verify. It's a very simple exercise that if you write out the Jacobi identity, you can rearrange it in a way that is precisely that. That you act the bracket with x on yz. What appears on the right hand side is precisely bracket of x acting as a derivation with respect to the bracket itself. So it is that form of the Jacobi identity is trivially easy to generalize for higher arity brackets, right? Because all you have to say is that you fill in n-1 arguments of an n-array bracket, and that acts as a linear map on your algebra, and all you're demanding is that linear map behaves like a derivation with respect to the bracket. And you ask, what is a derivation of an n-array operation? Well, of course, it's just you write out the Leibniz rule for the product rule for a derivation, right? So you just write, derivation on the first argument plus derivation on the second argument plus derivation on the third, and so on, right? So that's how you define what's called Filipov algebras. Some people, I myself call them just n-array algebras, just plain. And so what is fascinating is that in the same way that we know that the algebras are infinitesimal counterparts of Lie groups, we have no clue whatsoever what ternary algebras are the infinitesimal counterparts of, right? We just have no clue. And ternary or quaternary or quaternary doesn't matter. Like for n greater than 2, we have no idea with an n-array algebra is the infinitesimal counterpart of, right? So to me, it would be very interesting to know that there's this very simple operation that given DAGs give you a Lie algebra. It'll be super fascinating to see if we can similarly, with similar ease of construction, get something that builds a ternary Lie algebra. The ternary algebra, by the way, if people are thinking, oh yeah, that's a nice argument you have there, but that's kind of an abstract construct, I don't believe. Actually, everyone in high school saw the pattern that builds into higher arity algebras, because everyone learned that the cross product can be expressed like a determinant, right? So the cross product is a Lie algebra, a conventional binary algebra, and everyone understands that you can put x, y in vectors, and then in 3D there's a perpendicular direction defined by the two vectors if they are non-collinear. That is unique. So and so the direction is unique, and there is a unique vector that is oriented positively with the other two in that unique orthogonal direction, right? So if you stop to think for a moment what you did there with that geometric interpretation of the cross product, you realize, wait, that is not specific of 3D. I've been told a lie. They told me that I can only define the cross product in 3D, which is true if you want an actual binary algebra. But if you go to say 4D, you apply the exact same argument. You say, well, I have 4 dimensions, so you give me 3 vectors. So if they are linearly independent, otherwise it just gives 0. But if they are linearly independent, there is a unique orthogonal direction to all those 3, and there's a unique unit vector oriented in positively with respect to the 3. That vector is the output of the quote unquote ternary cross product of vectors in 4D, right? So that thing is a ternary algebra. If you check the axiom, that checks out. That is a ternary algebra. So you have, for any n-dimensional Euclidean space, you have an n-1 Ari Lie algebra lying around. So it just so happens that for 3D, we have our conventional rotation SO3 Lie algebra.
Yeah.
Actually, if you think about it, for 2 dimensions, in the Euclidean space, in the 2-dimensional Euclidean space, you think, wait, what is going on there? If it's n-1 Ari, I have a 1 Ari, so unary operation. What is the structure there? I mean, for the audience can check as an exercise, that's the complex numbers. That structure in the plane is the complex numbers. So it's a real plane, it's a real metric plane, which everyone knows the complex numbers can fit into, right? Because you have a norm and you have R2 in the background of C, so to speak. And so if you think about what rotation by I complex units means, is precisely that, right? You take one direction, if it's non-zero, meaning it's it's linearly independent, there is a unique positively oriented orthogonal direction to that, and that's precisely rotation by 90 degrees on the complex plane, right? So anyway, this slogan, this 2-minute slogan about hierarchy of the algebras is to say that these things are supernatural. They are extremely natural to define, and I'm just now burning with curiosity to know if, since this seemed to come up so spontaneously out of a context-free graph replacement, kind of graph splicing sort of formalism, I'm just super curious to think, how do you get out ternary algebras in a similarly simple splicing way? Anyway, just to pose it that I never saw such a clear question to get into ternary algebras, and yeah, it'd be very interesting.
There are a couple of questions from the chat here from Eric. So I don't know, Carlos, if you want to read them.
Yeah. So the first one was very specific to the context of the G1, G2 construction with the product. So the answer is basically I refer to our discussion above, right? So it needs. So there is a lot of. I'm sure that question was partially answered by our discussion that there is a lot of under hood technology that needs to go there to make sure that it is well defined and things go nicely. So you could think of it as proper rewriting, in which case we can just implement it with our functions of our hypergraph pipelet, or you can think of it as whenever it's defined, you throw it into the output, and if there are more than one, you throw it into the formal sum. Okay, there's a couple more. So if I understand correctly, the graph you were building in the last half of the talk could be applied to the associativity axiom ABC, ABC. If so, in so doing, would we get the associated term? So that's a question for Fernando, but
What was the question again?
So it's in the chat if you want to.
Okay, let me.
In the Zoom chat.
Okay.
No, so associated it's a different notion. It's not what we are considering here.
I think you can get it if you just apply the rewriting rule, right? Given the initial condition, like with a bunch of A, B, C, and D's, and you apply associator, you'll get the shape. I think that's what basically the question is.
Your thing. Yes, I mean, yeah. If you apply it to the right shape, sure. But
well, not the shape, the initial condition, right? You just if you have just A, B, C, D with one set of brackets, and you just try to apply associator in all possible ways, you get the all possible associations.
Oh yeah. I mean that's what I mean by the shape, like the initial state. Yeah.
Yeah, initial state. Yeah.
Yeah. All right. Well, that was super fascinating. Well, Fernando, I actually look forward to having some meetings one-on-one and working on this. By the way, just to follow up on the thought, the, otherwise I might forget, the if we think very briefly about this question of what it would mean to have a higher arity the algebra, right? Like the idea is if you want to be completely analogous to what you do in the case you presented, you want something like a formal sum of ternary products of graphs, right?
Right.
So it might be that you need to do something, because of course splicing is naturally binary, right? And it's naturally sort of pointwise associative, right? So in a way, perhaps it is surprising that the product ends up being Lie, but maybe not so surprising in some sense, right? Because at the end of the day, you're doing some kind of trickery of this sort of pointwise associativity is being smeared in the formal sum and like eventually conjuring up the Lie property. You know, it's still very interesting that it happens, but in my view, but so I'm trying to think of something, because obviously you can just say, well, let's splice three graphs sequentially, and that's exactly what you do to talk about associativity or the Lie property. So that's not good enough for ternary. You need to do an operation that is somehow indivisibly ternary, right? So you want something like splice a graph into a graph and then a third graph into both, right? Something like that.
Right.
So I don't know. I mean, it could be. I mean, it could actually be not that difficult to define in the sense that, you know, the first splicing is just the same splicing as you define, and then the second, and then that's a new graph, and then the next splicing is it's just a 2-point splicing, and it just is aware of the fact that you're splicing one vertex of one graph and one vertex of the other graph. But otherwise, the splicing procedure is the same, right? It's basically just identify one vertex and so on. It's the same construction. I have no idea if that is going to lead anywhere, but that seems like something, you know, you can
Worth
imagine.
trying, right? I guess.
Again, say it again.
It's worth trying.
Yeah, definitely. So anyway, I'm just saying these things here just to emphasize that there's definitely ways to go forward. So I think, you know, the path into higher arities and higher order here is twofold. On the one hand, we can try to see how much you can get out of graphs into ternary algebras or higher arity algebras. And on the other hand, you can ask what happens when you throw in hypergraphs, right?
Yeah.
So my intuition actually is that if you throw in hypergraphs and you do the same thing, my suspicion is that you get the same behavior. Like if you do a pairwise splicing like you do, I actually think that you probably get the same behavior. So because honestly, if you think of hypergraphs as line graphs, so as how do you say, as bipartite graphs, right, with two kinds of vertices, basically by replacing every hyperedge with a set of lines, set of binary edges. The procedure applies, right?
Yeah.
Like the procedure is completely preserved. Like just the splicing procedure applies verbatim. So I don't think you're going to find anything super fascinating just by kind of thickening your graphs and letting them to be hypergraphs. If all you do is just literally kind of like splicing in the same way. I mean, obviously it is an exercise to actually go through the proof and everything, but I don't know if anything changes formally. I don't think it does. But the other question, I find it quite interesting, and of course, what I find cool is that in the case of graphs, I mean, there are many ways in which you can say that graphs are can be composed in a ternary way like that. You know, like maybe you want to do some kind of like splicing, 3-way splicings and things like that, or maybe like another way could be to do 3-way identifications, right? Instead of identifying a pair of nodes from 2 graphs, you could identify 3 nodes from 3 graphs, right? And on the same vertex, right?
Right.
So that would be another 3-way thing. But what I find interesting is that it might be that there are some classes of ternary hypergraphs that are more natural to this sort of 3-way constructions. But anyway, I'm just speedballing here. This is all very interesting, so we'll talk. Fernando, don't worry.
For sure.
Yeah, but anyway, I wanted to give you some room at the end to say some final thoughts, or well, and if any of you guys have any questions or final thoughts before we close up.
Yeah, I think we were good. Yeah, that was a great presentation. Thanks for your time.
Yeah. So Fernando, you want to say some final thoughts, comments? Floor is yours.
No, I think I have already said pretty much everything I wanted to say. But thank you very much, Carlos, for your thoughts. Yeah, I will definitely think about it.
Yeah, no, exciting times. Yeah, I'll be in touch.
Alrighty. Thank you, Fernando.
All right. Thank you very much, everyone, for another live stream. See you in some of our